Welcome. This is the Learning and Understanding of Simultaneous Observation, or SIMO, using the Sun supporting the Flat Earth model. And you can receive a digital copy if you email me, Corey Kell, at corey7fe@gmail.com if you'd like a digital copy of this presentation. Mission statement: to educate and provide information on simultaneous observation using the Sun to determine Earth's true surface shape through the use of triangulation methodology. In essence, it's a form of map resection using the Sun. It was determined through lack of information available on the net, as well as within the general public, educators, and the Flat Earth community, the need for understanding and education on this subject. Simultaneous observation can provide direct evidence of Earth's true surface shape if we only understand the use of the Sun in this project. The Earth's true surface shape is the reason you see the Sun in the mid-morning sky position at 9 a.m. and not at the sunrise position at 9 a.m. because it's flat. What is simultaneous observation, or what is SIMO? Simultaneous observation is the simple act of, through visual lines of orientation, seeing the same physical or projected object by two or more people at the same time. This act can be at the same or different locations. The learning objective: this is a knowledge share and educational tutorial on the use of SIMO triangulation methodology using direct sun angle to determine by direction, distance, location, Earth's true surface shape. Additionally, we can determine the Sun's actual distance. In November of 2019, I attended the International Flat Earth Conference at Dallas, Texas. What a great event. There were around 500 to 600 people there, included interest groups, media. All were in attendance, people from all walks of life and children. Conference events were held for 2 days with a variety of speakers covering the proofs and evidence of flat Earth. I made a soft introduction at the conference and was interviewed. Learn, live, and love, the 3 big L's. We learn to live with one another and love one another. We learn the sciences, nature, plants, animals, and mathematics, the world we live in, the humanities, people, culture, religion, art, and music, the fun stuff. Live in harmony and peace with each other. Some of us don't do that so well. We love each other and treat each other with dignity and respect, and know that family is our strongest bond, and to care for one another. Why I believe we're really here. We're here to learn. This is a place of learning. My exposure into Flat Earth came in 2016. I had listened to Mark Sargent's Flat Earth Clues via the internet. For me, this was an eye-opening, well-put-together documentary. And the documentary I saw was called Under the Dome. I think it was a sub on a sub-channel. Much of what I had already experienced in life, I reviewed as I did my own investigational work into the subject. And I looked at areas that I already knew about, which were long-distance imagery, line of sight. I was a military person, so I knew artillery survey. That was my background. Hasty astro survey techniques using the sun and star, what we call sun shots or star shots. The horizon line and how it changes, or as it comes up, as it goes down, that horizon line remains steady. Richard E. Byrd expeditions, the polar expeditions, especially in Antarctica. I read all about those, Operation High Jump. And then the U.S. Soviet aerial nuclear tests, Operation Dominic and Operation Fishbowl in the 50s and 60s. We're going to talk about both models. We're going to talk about the heliocentric model and the geocentric model. We're going to apply SIMO to both of these models and show you the differences and what to look for and how to do it and the end results. We're going to use what's real. We're going to use the Sun to validate the Earth's surface. And if there's one thing that I want you to remember in all of this, and that is the Sun is your biggest ally in using or validating the Earth's Earth's surface. We're going to look at visual lines of observation, both intersect and parallel. We need to know those differences and what that means. One of the first recorded SIMOs in history by the Greeks. We're going to look at Aristophanes, who was a Greek and did one of the first recorded SIMOs in history. We're going to look at the military science applications. The military is full of, their manuals are full of information on triangulation, methodology, and use of simultaneous observation and mapping resection. It's all over in the military manuals, especially the United States Army. The human body, the protractor and tripod, and our sight limitations. We're going to look at those as well. We're going to talk about sun angle, time, and position. Time is kind of a key element. It kind of hints us as to where the sun should be, and based on time and position. We're going to talk about the check angle process, what we should really use to determine the Earth's surface, not sticks and shadows. We're going to actually conduct the SIMO setup and compare both globe and flat Earth models. In this setup in SIMO, I'm going to let you take a look at as far as the results and what can happen. We're going to look at Operation Resolute Time, which is ongoing currently, which is a rehearsal of getting timing and initial solar observations for sun angle and at specific times. So it's very important because that will lead us into Operation Golden Lance, which is a planned one of the most longest distance observations in history, solar observations in history. And we want to conduct a SIMO with 2 observers over 3,000 miles apart. Well, that will lead, Resolute Time will lead right into Golden Lance. And we're going to talk about the actual sun distance calculation. We can actually calculate the sun's distance using SIMO and triangulation. Very simple process. And the math that we do here is basic geometry. It's very simple geometry, 5th grade level. We're going to talk about using the sun, the #1 proof, how the Earth can be proven as a flat surface, how we can validate that surface. And if there's one thing that I want you to remember, and that is the sun, right here, this is your biggest ally, your greatest ally in proving the Earth's true surface shape. Flat Earth has the air power. The sun, use it. And that would be like, and I want to give you an example, and that would be like in World War II, the United States had air power in World War II, and it came to enforce that will over the Axis elements in World War II and helped us win World War II. I want you to know that Flat Earth, you have the greatest ally in this fight. Use it. It's the sun. The globe model must demonstrate the curve at long distance, or 145-degree sector, and we'll talk about that later on. There are 8 45-degree sectors in the globe model. We only need to test one to check for its validity. We want to avoid low-altitude atmospherics, things like refraction and globe-Earth mirage effects excuses. And I know a lot of people are out there doing laser tests and imagery at low level observations. Again, there's going to be a lot of interference with those, and weather has a lot to do with it, weather and temperature. So again, we want to kind of get away from those things, and we want to use our greatest ally, the sun. Use the very basic solid principles of geometry, triangulation, with applications of artillery and hasty astro survey. And we're going to use what we physically stand on and what we physically see to validate the Earth's surface. Use of the sun as an observation point. What I want you to know is the sun, it's small, it's localized, it's a mover, and it's really close. It's right around 3,000 miles. Using the sun and triangulation methodology, we can determine Earth's surface shape by using the sun. The sun, we're told, is about 93 million miles from Earth in the heliocentric model. This, however, cannot be the case, especially when we can perform simultaneous observation from 2 observation points on Earth's surface over 3,000 miles apart, with one being at 90 degrees and the other at 45 degrees. These observations are what we physically observe, measure, and document for record. In other words, what we physically see and what we physically measure. The angle of 45 degrees makes this impossible for the sun to be of any great distance, but rather a distance of just over 3,000 miles. The observable object or its projection in our sky is very close distance-wise. The 45-degree angle validates this as it intersects with the 90-degree guide angle. Hence the importance of having 2 observation angles with the guide angle of 90 degrees. This also again tells us that the sun is both relatively small and it's a mover. We need to know some terms when we talk about simultaneous observation. And we need to understand those, what we're talking about. And you're going to hear some of these terms, and we're going to kind of define some of those terms. The most important thing when we're talking about simultaneous observation is the guide angle to the EOL, or the sun. And EOL stands for end of orienting line, and this is kind of a survey term. We're using the sun in this term as the EOL, or the object where we're going to end that orienting line. So the guide angle to the EOL, this is a 90-degree measured observable angle from the Earth's surface to the sun from the observer. The guide angle sets the geometric right edge of the triangle. So we're going to set that right edge right here from the observer 1. We're going to set that right edge of the triangle when that sun moves at 90 degrees over us. All calculated distances, angles, and objects are within this set parameter. The guide angle observer controls the event and is called the master station. Again, the observer 1, this individual controls the event in the simultaneous observation. And you have the flank station observer 2. Observer 1 is going to set that right edge of that triangle. Notice that with our baseline, we're at the same elevation. We want to be close to sea level as possible. Doesn't matter whether our surface, whether we consider the surface flat or curved, we're at the same elevation. We're going to get the same result. The end of the orienting line, the EOL, or the sun, this is the EOL. This is the object that has been designated the end of the visual orienting line from the observers. This object is within the observed surveyed triangle from 2 dedicated orienting observation stations at the same time. So what I'm telling you is the sun is within this triangle. This is the EOL, this is our EOL. Both observers sight in on it at the same time. One at 90 degrees, this observer 1 sets the geometric right edge using what's called the guide angle. And we get our check angle from our flank station observer once observer 1 announces that it's 90 degrees, he or she is at 90 degrees to the sun. Timed observation and sector distance validation. Okay, we need to know this. In other words, how do we know that the Earth is actually 24,901 miles? This is kind of what we're told. So we've got several different measurements on the Earth, but the one that I find most frequently is this number here. And we're going to break down the globe. We break down the globe model into sectors. So there's 8 45-degree sectors. And each sector is just over 3,000 miles if we break it down by 40, which we did by 45-degree sector. So we're going to break it down. We're going to test one of those sectors. We only need to test one for its validity. This is a timed observation event. From 2 observers, the 45-degree sector will be validated for distance. The sun movement is 15 degrees per hour. So 15 degrees per hour, it has to move across this sector. So each sector, it moves, takes 3 hours of time. So if you add that up, it's 24 hours. Okay. The master station starts time. Okay. The master station, which here in this example would be Mazatlan, Mexico, starts time when the sun is 90 degrees to the observer. That starts the time. The sun must be at the flank station observer at the 3-hour mark. So in other words, it has 3 hours to move from one observer to the other, and it'll be timed. Okay. The difference will be recorded for record. The documented difference will be applied to the forward sun angle reading for record as a correction factor. And we'll kind of talk about that a little bit later on. But if the sun doesn't reach this observer at the 3-hour mark, if it's short, there's going to be a correction factor that needs to be added. So in other words, this distance, this sector is long. It's too long. In another case, if the sun travels from here to the from the one observer to the second observer, and it exceeds or it goes by and it's not 3 hours, at the 3-hour mark, the observer will measure at that angle. That will be a correction factor. In other words, this sector would be short then. Okay, so we're checking for sector distance. We have to validate the distance in order to make sure that this model is correct. And we'll find out. We'll be able to tell by the millimeter. The 45-degree sector test box, and this is how we're going to test the sector. Okay, the 45-degree sector test box is designed to do just that, test the curve. The globe sphere model cannot exist or survive without the 45-degree sector curve. There are 8 sectors in all. We need only to test one sector for its validity. The globe's 45-degree sector must be validated in both distance and surface angle. This is a timed observation event. The sun must travel between observers from the 90-degree mark at 3 hours. The sun travels again at 15 degrees an hour. So if we take a look at our test box, we have 2 observers, the master station observer, the flank station observer. We have our set distance, just over 3,000 miles in sector. Okay, so when the sun initially starts here, and when it gets to 90 degrees to observer 1, they're going to say mark your observation angle, flank station. They will measure that sun angle from the flank station to the sun. It should be right at around 45 degrees. Once the flank station observer does that and records it, they'll track the sun, and the sun will move between sector. It has 3 hours to get to station 2 or flank station and be at 90 degrees. Again, if it falls short, then we're going to take this measurement, the flank station, what will happen at the 3-hour mark, if it's right here, the flank station will then go ahead and they'll take the degree reading from 90 degrees and they'll measure where the sun is at in sector. So if it's short, let's say it's short, and they get a reading, they measure this angle from here to, let's say the sun is here. If that's 5 degrees and their initial reading was 40 degrees, then that 5 degrees would be added on to the initial reading, making it 45. In the other case, let's say if the sun surpasses this observer 2 and it's still not 3 hours and it reaches 3 hours here, and we had an initial reading of 50 degrees, and we got a reading here of 5 degrees. We went from 90 to 95 degrees. We would take that 5 degrees and we would subtract it from the initial reading, which our initial reading was 50 degrees. Subtract 5 degrees from that, that would be 45 degrees. And that's how that works. That's your correction factor. Both observers will record directional sun angle. So when it starts here, the sun comes from the east in Mexico, Mazatlan, Mexico. The Hawaii station will measure it when it's at 90 degrees, and they'll wait. And when the sun is at 90 degrees, the master station will record a back angle reading. It should be close to 45 degrees. So we have our sector test box. Okay, and that's how we test for distance and angle. Again, surface angle, we're going to get that in this text box. Okay. Thing I want you to know, it's geometrically and physically impossible for the globe model to obtain a surface reading of 45 degrees or more and visually perform SIMO with a base angle of 45 degrees in sector distance. You then will have observation lines in parallel, not intersect. This is kind of a precursor. We'll talk a little bit more about this, but this, in all actuality, This is a model, this is a kill box basically. And it is it's designed to have 2 models go in, 1 model will only come out. The triangular sweet spot. Again, this is the test box. Okay, we have our sector, we have our both observers here at 90, here at here. We want to look at distance. Again, we broke the globe down into 8 sectors at 3,013 miles. If we measure anything short, if we were to do this test in the continental United States, it's about 2,500 miles, anywhere from 25 to 2,700 miles across the United States. We could use that. We can use that coast-to-coast test. However, it's not the optimal choice. We want to sit right at the edges of this sector. We want to maximize this sector out and actually test and get an actual reading. This is the green, or the primary zone. And again, if we use the continental United States or a shorter distance under that, we could use it. We just get a higher angle. Our initial reading sun angle would be higher. In the same instance, if we went outside the test box, we went beyond it, the sun would be at a lower angle. It would be very hard to tell. We couldn't distinguish it if there was a curve or other inferences based on distance or surface angle. So right here is our green zone, and we can use the green or the yellow zone. We want to stay within these areas, within that sector. Once we get outside that sector, then we have too many other variables within that test, and we don't want that. This next section we're going to talk about is lines of intersect versus lines of parallel. Okay, lines of intersect were these lines of observation, they intersect. Okay, and here we have lines of parallel, they parallel each other. And we're going to talk about the differences and how we can tell. Okay, lines of intersect. Lines of intersect, the observers visually see the same object. Here we have observer 1, observer 2. We're both looking at the sun. Our lines, our visual lines, visually intersect. When you do SIMO, we both see the same object at the same time. Notice this is a natural triangle, flat surface, natural triangle. Visual lines of intersect from 2 observers. We're seeing the same object at the same time. Lines of parallel. Okay, observers are no longer looking at the same object. So I have observer 1, observer 2. Our surface is flat, but we're not looking at the same object. This observer here is looking up, straight up, but that object is not, we're not looking at the same object. So that's at 90 degrees, 90 degrees. We have visual lines of parallel, or what we call, what is also called the goalpost effect. Lines in parallel. When the ball or curve is introduced, we need to understand what happens. What happens when we introduce a curve, okay? The observers are no longer looking at the same object. Visual lines of parallel happen when the ball or sphere is added to the observer angle of view or line of sight. So here we have the flat surface, okay? We have 2 observers looking at the sun. Originally, we had the initial 45-degree natural triangle right here, okay? Now, when we introduce the ball or globe curve is applied, our line of sight changes. As we cant off to a 45-degree angle, now we have the original line of sight that was 45. We have to add the curve. This was a 45-degree curve, a visual line of sight. Now we have lines in what? Parallel. So, when we look at lines of parallel, we are 45 plus 45 is 90 degrees. We're no longer looking at the same object. We need to understand that. Let's take a look at science's foundation work, some of science's foundation work when we talk about simultaneous observation. And one thing, if we look back into recorded history, the Greeks recorded one of the first simultaneous observations, or SIMO, in history. And we're going to look at an individual named Aristophanes. Aristophanes was known as a foremost scholar in his time, produced impressive works of astronomy, mathematics, geography, philosophy, poetry. He was key in the development of method of finding prime numbers. So this guy was a major mathematician. Really a smart guy. Big cranium on that guy. A lot going on in his head. Aristophanes was Aristophanes' most famous accomplishment is his measurement of the circumference of the Earth. He recorded the details of this measurement in his manuscript that is now lost. So we kind of highlighted that. We underlined that. That's kind of a red flag. We'll keep track of that. But his technique has been described by other Greek historians and writers. We kind of get into trouble when we allow other people to tell our story. But we'll keep track of that. One of the best documented methods for determining the Earth's roundness was first performed by the ancient Greeks. This was achieved by comparing shadows of sticks in different locations. When the sun was directly overhead in one place, the stick there cast no shadow. At the same time in the city 500 miles north, the stick there did cast a shadow. And they're talking about from Aswan to Alexandria, Egypt. There's 500 miles. This is our difference between those. Okay, so that's a good setup. I mean, the setup is really good. This first paragraph makes a whole lot of sense. Now, where we start to go off on a tangent is in the second paragraph. If the Earth were flat, then both sticks should show the same shadow or lack thereof, because they would be positioned at the same angle towards the sun. Okay, that's wrong in so many ways, but we'll discuss it later on. The ancient Greeks found that shadows were different because the Earth was curved to calculate the circumference of the Earth. Okay, let's talk about that. So this is the setup. Let's take a look at Aristophanes' setup. So we have observer 1 right here in Aswan, Egypt, and then observer 2 here in Alexandria. The sun is at 90 degrees, or right over the first observer, the stick. And again, didn't cast any shadow. But we have to remember, we have what? We have distance. So now we have sun angle. This stick is going to be at an angle to the sun. So that's just natural, okay? So right there, we have a problem with that second paragraph, what the statement in the second paragraph is. But we need to understand that and know what's going on. So let's get into it a little bit more in depth. Sticks and shadows is not the method to use for this observation. And when you determine Earth's surface, you want to use direct sun angle. If you're going to use shadow angle is only good to telling you the object what degree it's standing in. So in other words, this shadow is at this stick is at 90 degrees. Both of these sticks are at 90 degrees, and we'll talk about that. Here we have, again, as I said, they're 500 miles in difference apart. We have the sun over the first stick, and the second stick is at 500 miles. So there's a difference. The angle is going to be very high from this stick to the sun. You're going to have, if our shadow angle is 7.2 degrees, we're going to have a sun angle of 82.8 degrees. So this angle is going to be high because this is a very short distance. Remember, the sun is at the 12 o'clock or the 90 degree position. Shadow angle is not the method you want to use for determining surface angle, specifically Earth's surface angle. Use direct sun angle. Shadow angle plus the angle, angle plus the sun angle equals the sum of the object 90 degrees at the vertical angle. So in other words, if we add 82.8 degrees and 7.2 degrees, it's 90 degrees at the stick. That makes sense, and that works. We can test that, and it works every time. Why I believe they lost Aristophanes' notes in his manuscript. They were worried about direct sun angle. They're worried about this figure here. Aristophanes figured out that the Earth was flat from sun angle. It's basic triangulation in geometry. And again, this is why we have the what? The heliocentric model gap from Aristophanes to Copernicus. It didn't take hold because people shot holes in it and said, hey, use direct sun angles. Another factor involved in this is we have to know our elevation. You know, what our elevation from our observers are. And here in Alexandria, Egypt is at approximately 5 meters above sea level. Aswan, Egypt is right at 194 meters above sea level. Difference of 189 meters. Not a big factor, 0.01 factor if we're looking at calculating. So not a real big factor, but we need to know that this experiment was not at the same level, elevation-wise. Aristophanes, we're going to look at, okay, when we talked about the 82.8 degrees, so we put our protractor on it, we get our 7.2 degree shadow, and our sun angle, of course, is going to be very high because why? Our distance is very short. Okay, so the sun is casting a very small shadow. No shadow here, very small shadow here, high sun angle here. Use the correct vertical sun angle measurement, okay, which would be 82 degrees based on the shadow. Do not use shadow angle when you have direct sun angle available. Use the check angle process of measurement. And this is why we do that. So again, we don't use sticks and shadows. This is why we don't use sticks and shadows. It gives us a false read. Let's take a look at military science application. And the military, when we talk about triangulation, resection, and survey methods, it's all over in military science. And when we talk about SIMO applications and triangulation, it's geometry and basic application and principle. It's within a lot of the U.S. Army military manuals. When we talk about survey operations for the U.S. Army Field Artillery, lay the cannon battery for indirect fire, they're using SIMO and triangulation. It's all over in these manuals. And you'll look at how they determine triangulation and how they set it up. And again, with land navigation, resection, by the U.S. Army Land Navigation, find your location. It's references. These are the manuals you can find them in. And it's all over in these manuals. And the U.S. military uses it because it works. It is not theory. They have to do practical application. And I would do, when I was in the airborne artillery, I would do sun shots, or using the sun, or star shots, and I would set in my own survey. Use what's real. Sticks and shadows, the U.S. Army uses it, the military, and it's in the Soldier's Manual of Common Task. This method can be found in the Soldier's Manual of Common Task, and it's, again, used for directional use only. Directional use only. And basically how it works, we're going to start here with this diagram. This comes out of the Soldier's Manual of Common Task. We have the sun has to be at an angle. We put our vertical stick in the dirt, and the sun casts a shadow. We're going to put a mark at the end of the shadow, or put a stone. That's our first mark. We're going to wait about 10 minutes, and then we're going to get a different side picture. Now this first mark, this is going to be our west mark, or our first stone is our west mark. As the sun moves from east to west, the shadow is going to move what? In the opposite direction. So here was our first mark. 10 minutes later, here's our second mark. We put a second stone. We put our second stone in, that's our east mark. We draw a line. Okay, that's our east-west line. Now we can draw our north-south line just right across from it. And now we have our direction. We know our direction. And this is what sticks and shadows should be used for only. Bust the myth. The check angle process of measurement. This is what we want to use if we're going to determine Earth's true surface shape. To achieve the correct check angle of measurement incorporates triangulation methodology. Use of two observers from different locations simultaneously. Known distance between observation points not to exceed 145-degree sector of the Earth's surface. Why? Because we're using the sun. This is to ensure that Earth demonstrates her curve in the process. Excuse me. Surface angle or degree between two known points. We need to know that. And we want to be on the same elevation. The primary observation should be at the 90-degree guide angle to the measured object, in this case the sun, which is the end of the orienting line. The angle to the observed object from the second known point is used from our flank station. That's going to be our check angle. Both known observation points should be at the same base elevation. We want to use as close as possible to sea level. And check angle result will be computed, again, from the flank station. And this is the process what we want to use. We do not want to use sticks and shadows. This is the process we want to use. The check angle process of measurement. Let's talk about the human body, the amazing human body. We have a natural protractor and a tripod built in our human body. Well, let's talk about that. The human head is the protractor. It physically moves in the direction or angle we want to see an object. So if we move left to right, it's like a protractor. We're moving left to right. If we look up or down, again, it's like a protractor. Whatever direction our head moves, it's a degree. It tells us what degree we're moving. Okay, and that's our built-in protractor, the human head. The body is our tripod. It physically stands on the surface of the earth in the desired direction, but it also connects us to what? The protractor. And I put in the little belly button thing here. The belly button or the navel is our 0 degree line. It physically faces in the direction when upright and standing. It parallels the surface that we're standing on at whatever degree or angle. So you're going to see these 3 cardinal angles, and we're going to talk about them a lot. The 0 degree angle, that would be our belly button. It parallels the surface of the earth. The 45 degree angle, that's halfway between looking straight up, or our guide angle, which we look skyward, or a 90 degree angle. So 3 basic angles, 0, 45, and 90. And we're going to try and keep this as simple as possible. What we need to know is the movement of our head, or the protractor, is the recorded upper motion. We physically view an object. This is also called the check angle measurement. So when we look at an object, whether it's at 45 degrees and we see an object up here at 45 degrees, this is our check angle. We're checking it. We're looking at that object. We move our head. The position of our body or tripod, whether on a flat or curved surface, is the recorded lower non-motion. So our body is on the recorded lower non-motion we physically stand on. At any angle our body or tripod is physically on must be added or accounted for along with the recorded upper motion. So again, this is where a lot of people don't get the curve, how the curve affects. If you talk to them and say, okay, we have a recorded lower non-motion. We need to keep track of both of these. They are factors. We talk about our human head. Lifting your human head to view an object is a recorded upper motion, as is in this diagram right here. This individual is lifting their head to look up at the sun at a 45 degree angle. You must physically view the object, whether you're on a flat or curved surface, so that head elevates up to look at that object. All right. This is the recorded upper motion. All right. This must be added along with the recorded lower non-motion angle of your body to obtain a true composite angle. So in this example, like I said, the individual is looking at 45 degrees on a flat surface. Right over here, we give the example. Looking at 45 degrees, the upper recorded motion, lower recorded non-motion, flat surface, 0 degrees, so 45, 0 is 45 degrees. All right, that's how we do that. Very simple, nothing very difficult. Our human body, our tripod, and recorded lower non-motion. Okay, on this example, we have the individual at a 45 degree angle or on a curve. Okay, so their head and eyes are straight. They're not lifted, so they're at the 0 degree angle. So again, we have 0 and 45. All right. Whatever angle degree your body is on must be recorded. This must be added along with the recorded upper motion or check angle to obtain true composite angle. So again, we've got 0, and then the lower recorded, we're on a 45 degree angle or curve, which equals 45. Okay. Nothing difficult, pretty easy. Check on learning. All right, question. With a measured recorded upper motion of 35 degrees and a recorded lower non-motion of 20 degrees, what is the total composite angle that the observer records to the observed object? Would it be A, 55 degrees, B, 75, or C, 65? If you said A, 55 degrees, You were correct. We just add 35 and 20, it's 55 degrees. Too easy, right? Now here's an interesting subject, and I put this in as an added section to the original document I produced, and it's called Identifying Human Visual Sight Distance Capability. And this was brought in specifically because there are some people that will tell you that lines of intersect and lines of parallel are kind of one and the same. So we're going to kind of bust that myth, and we're going to take a look at how we deal with that. So we're going to identify human visual sight distance capability. You have physical limitations. We as humans, we don't like being told we have limitations, but we have them. Like the little girl, she's not a happy camper right there. Science doesn't like it either. When we tell science they have limitations, they kind of throw conniption fits. So they don't like being told they have limitations. Visual acuity and sight limitations. Annually, you should get your eyes checked, and here we have like a basic eye chart. And if you look at it, we have lettering on the eye chart. Our eyes are by far the weakest design in the human body, and for good reason. We're not meant to see great distances beyond the design of our world. Our eyes are designed only to look, within this world, within this realm. We're not meant to see great distances. And again, this is a basic eye chart. One thing I want you to keep track of, notice that there's almost kind of like a triangle formed in this eye chart. We have the bigger letters up top and then the smaller letters down below. It kind of forms a triangle. On this end, we kind of got the rectangle effect, or the open end, and on here we have the closed end. So just kind of keep track of that. Over here I put this chart in, and this is a black background with white object on it. It's letters and objects on it. Same effect. I want you to notice it's kind of a triangular effect. The open end has the larger objects, what we can see easily. As we refine or narrow in our point of view, it comes to a point. So just kind of keep that in mind. Here we see two different shaped objects, and as I said before, some people are going to tell you that these are actually one and the same object, the rectangle and the triangle. The triangle is actually an elongated rectangle as it goes out. The only problem is that the triangle comes to a point, okay? And when we reach that point, we've exceeded our sight limitation. That's what that means. The open end, or the open end of the triangle, we can visually see. Remember, the big letters, the big objects. So in this rectangle, we have everything that's large. We can see within that. Okay, we need to understand and know that. When we exceed our visual sight capability, we need to know when we've exceeded it. And how do we do that? When these two objects, the rectangle and the triangle, become one, our visual sight limitation has been exceeded. Specifically, when lines of intersect, okay, these would be lines of intersect, become lines of parallel. So somebody in science is going to come along and say, well, that object is out so far, it's actually lines in parallel. You've vastly exceeded your human vision capability. And that, again, the triangle end, science is going to want you to open that triangle end up to see that. But again, as we come to lines of intersect, okay, we're at a point where we've what we can visually see. But science is going to want you to open that up and become a line of parallel and say, hey, look, you can see farther than that. When in all actuality, we cannot. And how we can do this, we can do a check on learning. And this is how we put science in check. We can perform a walk-off test. So, design this black background pattern. You can take a card, get a black card, put white objects on it. Take this card or a piece of paper and then walk off your distance. And then start with your lower. Remember what we said, we had the triangle here, the natural triangle. All right, we have the smaller objects. As we move farther back, farther and farther out, distance-wise, these will disappear into what? The black. And then the next line will disappear into the black. And the next line, the farther we move back, each line will disappear into the black. And this is called the walk-off test. And this is how we can put science in check and say, no, we can't see lines of intersect. You know, we can't, lines of intersect and lines of parallel are not the same when it comes to vision. Okay, we have we've exceeded that sight limitation. Sun path, position, and time. Okay, we need to understand a little bit about where the sun is and the seasons tell us that, positioning, and also time. All elements that kind of give us clues. This is kind of a little busy diagram. Don't be worried about that. Okay, we're gonna take from the observer here, and the observer in the continental United States is facing east, looking at an early morning sunrise. Now, based on the season, okay, the season, if that sun is far to his left, okay, would be up in the north. Would be the summer season, the warm climate. If it's colder, of course, then that season would be what? The fall or the winter. Okay, so just kind of think of this as a sliding scale. The sun slides left and right as the seasons go. Okay, sun movement maybe to the left or right based on the observation location and season. Extreme northern and southern latitudes will have the most severe angle. The seasons will tell us information if the sun is in the northern or southern latitude, or northern or southern is in the summer or spring season. Okay, if the sun is in the southern latitude, it will be fall and winter. Okay, so again, if it's in the warmer to the left, it'll be center left. It'll be the summer and spring. Far right will be the fall and winter. Kind of pretty easy, and you kind of watch this. You can watch this as you're wherever you're at from home, or if you're at a place that you always like and you kind of notice the seasons change. Watch the sun and the sunrise, where the sun is at, where it starts from in the morning as it goes across the summer sky. And what I want you to know is we've got the protractor here. Again, we're talking about the 3 cardinal degrees: 0 degrees, 45, and 90 degrees. And if we look at this from the observer, okay, early morning summer, about 6 o'clock, 6:30, that sun is gonna be at what? At 0 degrees, right at the horizon. Right at the horizon. Okay, at mid-morning, 9 o'clock, the sun is gonna be where? About 45 degrees from the observer in the sky. And then at noon, the sun is gonna be what? Right overhead. It should be pretty close right over our head at 90 degrees. So that sun moves across us in the sky throughout the day. Okay, so here that's talking about sun path and movement. Sun position and time. And again, this is continental United States, summertime. We have the sunrise. Okay, the sun is at the horizon. Okay, here's our horizon right here. Okay, sun position in our morning sky at about 6 a.m. hours. The sun is at the 0 degree angle viewed from the sun. So this is our sight picture. This is what we would see. Now I'll give you a hint, okay? 0 degrees here. I will give you a hint. If you believe that you live on a globe and you live on a sphere, okay, at 9 o'clock, you need to see this sight picture. This is what you need to see if you live on a globe, okay? And this is what you believed in. And then this was the sight picture, what you would actually visually see. Because what you're seeing is the curve. You're seeing the curve of the earth. And on the other side, you would have another observer. That sun would be at their 12 o'clock position on the other side of the curve. So this would be your this would be your sight picture if you believe you live on a globe or a curve at 9 a.m. in the morning. Some people are going, wow. All right, sun position and time. We're going to talk about the 9 o'clock on a flat earth. All right, morning sky, mid-morning sun. Okay, at the 45 degree angle. Okay, just over the houses and a little bit higher in the sky. This is mid-morning sun at 9 a.m., about 45 degrees. Again, continental CONUS, United States. This is on a flat surface. Again, and then at noon, we look at what? The 90-degree position. Sun is at sky high at noon, 1200 hours. The sun is at the 90-degree angle, okay, right over our head, okay? So we talked about sun position and time, what the sight pictures look like, what they actually look like, what we should visually see. Now we're going to talk about the SIMO experiment process, the process, very important. SIMO will demonstrate flaws in the globe Earth model. We've already talked about some of them based on sight picture, what we physically see in degrees. SIMO will demonstrate evidence to support the flat Earth model. And again, some people say, well, I don't believe the dome or whatever. Again, this is just, again, a flat Earth model. Some people don't believe that there's a dome. There are different models around, but we're talking about basically a flat Earth model. Action 1 or Act 1, we're going to do the actual setup, and this is a forward check angle reading from the flank station. Now we have both models on this showing here. Model 1 is the flat Earth model. Model 2 is the globe Earth model. We're dealing with the curve, okay? We take this curve right off a protractor. Let's talk about the flat Earth model. It's pretty easy. Our time at the flank station is at 09. Time at the master station when we do a SIMO observation is at noon, okay? 3,000 miles apart, okay? Both observers, we have the natural triangle, the right triangle. 45 degrees here, 90 degrees here. It's too easy, all right? That's the natural angle. That's the flat Earth model. Again, your surface is flat. What we visually view, the sun in the sky, is 45 degrees, how we measure it, the angle. Now, let's talk about the globe Earth model. And again, remember that same elevation. We're on the same elevation. So again, same elevation. Doesn't matter whether we're flat or curved. We're at the same elevation. On the globe model, now we have to deal with this curve, and this is where the curve works against the globe Earth model. And it really works hard against it. If you believe that you live on a globe, on a curve, you have your observer 1, the master station, again, 1200 hours, noon reading time. Flank station observer, 9 o'clock, okay, same times, 90 degrees to the master station. However, the flank station at 9 a.m. needs to see that 0-degree line, okay? And some of you will ask, well, why does it need to be at, why do I need to see a sunrise sight picture at 9 a.m.? Again, we have to contend with that, what? The 45-degree curve here, okay? And we're going to talk about that because that curve is going to come into play, okay? But if you believe that you live on a globe or a curve, then you need to see a sunrise at 09 o'clock in the morning. That sun at the horizon, okay? Because what happens if you get a reading, like on the flat Earth model here, if you have a surface reading of 45 degrees, you're going to be in trouble, okay? And why are you going to be in trouble? And we're going to talk about it. Because if you have a surface reading of 45 degrees, in other words, the flank station measures the angle to the sun at 45 degrees, whether you believe it's flat or curved, you read 45 degrees to the sun. If we add 45 degrees to the sun, okay, example, if we add 45 degrees to the curve to the upper motion reading, recorded upper motion reading of 45, we have what? 45 and 45, we have lines in what? Parallel. This line is at 90 degrees, this line is at 90 degrees. Now we have lines in parallel. That's why this model does not work. You do not live on a globe. You do not live on a curve, okay? The upper recorded motion reading is 45 degrees or more. This angle is then 90 degrees, which parallels the master station orienting guide angle. And this is why it's so important to have the guide angle at 90 degrees. This is what does in the globe. The guide angle really does in the globe, okay? And it's the reason it probably gave Copernicus fits, and why Aristophanes, why there's that big gap in those models. You know, they couldn't work through this. This is the test. The SIMO is what validates the Earth's surface. And you need to understand that, why those models failed and why they dropped off. Copernicus died, they released his model. Somebody else did it. Same thing with Aristophanes. Somebody else released it. Other powers in play. These individuals, they knew better. They knew that this model didn't work. All right, and again, we'll talk a little bit about the correction factor. You know, if the sun falls short, then we get a correction factor. Either way, short or long. And we have to add that to the original initial reading. So again, this is why we don't live on a curve, or we don't live on a globe. When we actually put it to the test, it fails. It fails the process. Act 2 or Action 2, we're going to, again, flat Earth model, globe Earth model. We're going to let that sun move across sector 3 hours, and we want to get a reading. When that sun is 90 degrees, we want to get that reading from the master station. Should be about the same angle as the forward angle. Again, if we're online, we're linear, then we want to do that. Okay. On the globe model here, again, you got to contend with that curve. It has to be 0 degrees in order for your model to work. You'd have to see a sun set at this time, because again, your reading time here is 1500 hours. Okay, and then 12 noon at the flank station. Remember, we're tracking the sun going from east to west. Okay. Sun distance perspective comparison. Again, when we look at it, and just to give you an example, the globe Earth model, they need that high ceiling. They need that 30-story building. Flat Earth model, just single-story building, low ceiling. When we look at both models, the globe model on the left, flat Earth model on the right, the natural 45, the sun path and distance over 3,000 miles apart. The heliocentric model, boy, they need all that space. They need that skyscraper for their model to work. But again, if you don't see that sun at the 0 degree line, your model is not going to work. Your model it fails. In the flat Earth model, we got the natural 45, like the triangle, the natural 45. Well, here we did the observation setup at Mazatlan, Mexico, and Hawaii. These would be our times, our observation times. And again, the globe Earth model here, lines of parallel. If they don't get that 0 degree reading at 9 a.m., which I've never seen a sunrise at 9 a.m., you're going to wind up with lines in parallel. You got line here from the observers. Okay, you have that. Remember what we talked about, that goalpost effect. And this is a sun, they say that's 93 million miles away. This is why their model doesn't work. Doesn't make sense. Again, the flat Earth model, still tracking. No issue with the 45 and the 90, the natural triangle. And again, lines of parallel. Somebody will tell you that lines of parallel intersect are the same. They are not. Okay, here's why the flat Earth model works so well. 9 o'clock, we have the 45 and 90. Again, like the guide triangle here. At 10 o'clock, we're at 60 degrees, the sun from the second observer. At 11 a.m., 75 degrees. And what? At noon, 3 hours later, 90 degrees. This is why the flat Earth model is so simple, so basic, so easy. It works. We initiated Operation Resolute Time, and in preparation for Operation Golden Lance. And the concept of operation and rehearsals to exercise to establish observation timing. The preparation for Operation Golden Lance. Observation timing is the key to establishing observation times, as well as initial sun angle indicators for future observation support for Operation Golden Lance. Initial observation started 7 February 2020, 12:37 Kabul, Afghanistan time. With a recorded sun position 90 degrees, observer north-south plumb line was established with the sun crossing the southern latitude to Afghanistan at 12:37 hours. So sun is way down yet in the southern latitude yet, but it's working its way north. But again, we measured that, or measured that angle to the sun, started observation. elevation location near Kabul is right at 5,960 feet above sea level. And again, Latin longitude, close to that, but not exact. Just gives you an idea where, if you know where Afghanistan is, and we're close to that. Let me see. I think I hit that. Okay. The objective, this is a timed observation event, anywhere from 3 to 6 hours. Some days we'll record it, we'll get initial readings, other days we'll record full time. Establish timing, we want to know where that sun is at when we get initial sun angles. Additionally, to record initial sun angle readings from the observer and line of sight placement of the digital protractor. We're using a digital protractor. And solar readings of we get two solar readings 30 minutes apart, one at 9 and 9:30. And this is all based on when the sun crosses that 90-degree plumb line. Operation Golden Lance, a future operation. This is going to be one of the longest or largest distance observations. And why do we want to set up on the meridian? We want to be linear. Okay, we want to be linear. We want to set up in alignment. So when that sun moves along the tropic, in this case the Tropic of Cancer, we want to be on that line. We'll get a very, very good reading if we're right along the Tropic of Cancer. 21 June, I believe, is the summer solstice. So we'll be 3,000 miles apart, Mexico and Hawaii, and we should get the natural 45 and 90. We'll probably come up even with a higher reading, I think. Right now, we've passed the threshold here in Afghanistan. We're over 45 degrees right now in that 30-minute bracket from 9 to 9:30. We're already at 46.5 degrees. So we've crossed the threshold in that aspect. So very positive readings. And it's only April. We haven't even reached the summer solstice yet. Again, equator, any one of these meridians would be optimal observation experiment setup sites. Golden Lance, concept of operation, perform one of the largest distance SIMO events of sun recorded history. The observation will be from 2 known sites over 3,000 miles apart: Master Station in Mazatlan, Mexico, Flank Station, Hilo, Hawaii. Observation times 1200 at Mazatlan and 9 at Hawaii. And again, we'll look at when the sun crosses that 90-degree plumb line. When it crosses that 90-degree plumb line, then we start the event and we measure from there and then start our timing. Primary date is 21 June. We actually look to do arriving somewhere around the 18th or 19th and do a day or two of practice and prep. And then the 21st will be the primary date. 22nd will be recovery and tear down. But if we need to do a final observation date, we possibly could do that on the 22nd. The objective, the timed observation event, 3 hours. The Earth's surface, 45 degrees sector must be validated again, both distance and surface angle. This will be accomplished using the sun as a distant aiming reference from both observation stations simultaneously. The goal, just to provide evidence of the achievable 45 degrees surface angle reading to the sun from the flank station. The 45 degree angle is key at over 3,000 miles because the surface curve of the said globe at over 3,000 miles is also 45 degrees. This would make it impossible to be a composite angle of 90 degrees, which would, again, we have lines of parallel. They would never intersect during a SIMO observation. In other words, we wouldn't be looking at the same object. Additionally, observation lines of intersect go parallel and exceed human visual sight capability, naked eye capability. A negative or below reading of 45 may indicate several findings. Sun is very regional, curved surface, or other known indicator. And we might pick up some drift because we're off the meridian in Hawaii. I think we'll lose maybe 1 or 2 degrees because the Hilo, Hawaii sits just below the meridian. But again, the primary location being Mexico is right on the Tropic of Cancer. I think we'll pick up some initial drift from the initial reading, maybe 1 or 2 degrees because of the drift, but other than that, I think we'll still be in very good standing. Additional instructions: take photographic and video documentation required during setup, sun position, sight picture, and final documentation or documented check angle reading to the sun from the flank station. So we want to record all that data. And again, why the Tropic of Cancer? Again, remember we talked about the meridians. It's sitting on one of the prime meridians, the Tropic of Cancer, and marking the latitude 23.5 degrees north, where the sun is directly overhead on the 21st of June. So that is ideal, an ideal site, ideal date and time. Again, we'll set up the test box, the Operation Golden Lance test box. Same thing. We're going to set that up. We'll have observers 3,000 miles apart. And again, the test box will be set up along the meridian Tropic of Cancer, master station along Mazatlan, Mexico, during the direct Tropic of Cancer. The flank station located in the main island of Hilo, Hawaii. There will be some drift, again, because Hilo, Hawaii sits below the meridian from the flank station reading. This is due to the location of the island just being south of the prime meridian. However, the reading test results should be still very conclusive, with one of the goals being to achieve the reading of 45 degrees or more at the edge of sector. So we want to be on the edges of that 45 degree sector. Drift will give slightly lower angle reading, like I said, probably about 1 or 2 degrees. We'll still be in very good standing. And again, here's what I talk about when we talk about location. Here's the Tropic of Cancer. You have Mazatlan, Mexico, master station here. We're right along that meridian. And again, we're sitting just south, so we're going to pick up some drift off our initial reading, okay, from the sun. We may pick up some drift because we're south. That flank station is south, so maybe 1 to 2 degrees. We'll see. We'll see what happens. And right now, we're having pretty good readings up here in Afghanistan. So again, 3,000 miles apart along the Tropic of Cancer, prime meridian, prime location, right along here. So I think if we're in anywhere in this area, it'll be absolutely optimal viewing. Accessibility, and again, it's during the summer solstice. It's when that sun is directly overhead that meridian. That's what we want. This is kind of the setup and how we set up. And this is, we're going to use a digital protractor device. This is a digital protractor, and it basically measures angle, and it'll give you an angle reading. It's battery powered. Basically, we're going to have a tripod set a ½ meter above the Earth's surface. And we'll have a plumb line. Actually, the plumb line will be right here below the tripod, but I couldn't really get a good view. And there'll be a marker on the ground. We'll get a GPS grid to the location. Each day, we plan on doing several days. We want to set up in the same site. Same setup. We'll note where the protractor is lined up on the tripod, or on the tripod and the base. The base is level. Again, we have to level the base. And there'll actually be 3 tripods set up. 2 for the plumb line, the north-south plumb line, and then 1 for the digital protractor. Same elevation is used, or near at close same elevation near sea level will be used. And again, flank station, Hilo, Hawaii, master station, Mazatlan, Mexico. Mexico and Hawaii, 3,000 miles apart. 45 degree sector, this is the sector we're going to test. We're going to use protective coated lens when we look up at the sun. We have a sun shield. We'll get into a little bit more of the setup, and this is what I talked about. We have 3 tripods. Here we'll have the north-south plumb line, 90 degrees. We'll set it in with a compass, and we'll set the plumb line in, and we'll just run a piece of string from one plumb line to the other. North-south, that's a north-south plumb line. And then the other tripod will have the digital protractor with the base, again, ½ meter off the ground. The plumb line will sit about 1.25 meters from the ground. Sight picture, this is kind of the sight picture we want to see from the master station. This would be the digital protractor. This is your north-south plumb line. So as your sun is moving from east to west, you know, that's going to cross this plumb line. This is center mass. This is when we start time. This one will start the 3-hour time, and we'll also get what? The check angle. The flank station will then measure, Hawaii will measure to Mexico the angle from the surface of the Earth to the sun. Okay. Accuracy on these digital protractors ranges from anywhere from 0.1 to 0.5 degree accuracy. A little bit more about the setup in the flank station, because they're sitting just south. When they look up into the sun of that north-south plumb line, the sun will be just to the right of on the plumb line as it moves across. And this is how you're going to kind of sit. You'll sit laying on the ground or looking up in the digital protractor. And that plumb line, you'll have that other plumb line that sits right across there. So as that sun crosses it, then you'll mark time. So it's pretty easy. And then again, when we measure angle or whatever, we're doing the same sight picture. We're looking up along that tripod or the digital protractor line of sight. And again, using digital protractor, we'll have a tripod-based vertical plumb line, mark the site, same location each day. And again, the master station controls the event. Plumb lines will be incorporated, declinated based on location. Mazatlan, Mexico is plus 3.5 degrees. Hilo, Hawaii is 9.5 degrees. The results, well, to be determined once we do the actual observation test. I said right now we're in Operation Resolute time, and I said we've already broken the threshold, 46.5 degrees. So very positive results even from Afghanistan. We'll track surface angles for each of these dates that we test. Triangle calculator, and we can calculate the sun distance using the triangle calculator. Real easy, and we can do this by setting in some basic factors, and you can find this calculator online. We know our base distance. We're at 3,113 miles. We also know our angle to the sun, so we can plug that in. We plug that in, it fills in the other ones. It'll give you the hypotenuse, this angle right here. Again, like I said, this angle here is 45 degrees. And then the hypotenuse, it'll give us the distance. It'll give us from the flank station observer to the sun is 4,010 miles, 4,410 miles. And then it'll give us what? The height. The height here, and it'll give us what? 3,123 miles to the sun. This is how we can calculate actual sun distance. And do you see? Does anybody see 93 million miles in this calculator? I don't either. So again, this is sun distance SIMO calculated. We can do this through simultaneous observation, and we can start plugging in our angles and our distances, and it comes out on our sun calculator. The sun is the actual distance if our reading is at 45 degrees. And I think we'll probably get a higher reading than that, somewhere in the neighborhood of about 47 or 48 degrees actually. And I believe that reading will be in Hawaii, but we're still going to be distance-wise 3,000 miles, right? Just a little bit over 3,000 miles. And again, our baseline distance over 3,100 miles. This is our sun distance calculator, how we can actually calculate sun distance. Mother Nature will reveal her secrets to the keen observer. She has a story to tell for those who take the time to listen and look. The earth you live on is flat. Understanding Mother Nature and our world. Summary, some of the things that we talked about. We used the sun to validate Earth's surface, and I wanted to get this information out, how to do it. And again, if you remember anything from this, and that is, use the sun. The sun is your ally, your greatest ally in the discovery of flat Earth. And it's so simple. This is actually very simple and very relatively inexpensive experiment to do. Those digital calculators, you can pick them up anywhere from $30 up to $100, $150, and depending on the model. We talked about the military science applications, military, U.S. Army. It's all over in military application, triangulation, SIMO, resection. It's all over in those manuals. Sticks and shadows, the myth, what sticks and shadows is actually good for. It's just for finding direction, sticks and shadows. So if you remember sticks and shadows, direction use only, not to discover the Earth's surface. We want to use the check angle process for that. The human body, the natural protractor and tripod, and our sight limitations. Remember, lines of parallel versus lines of intersect. Sun angle, time, and position. And we need to know those key factors. The seasons will tell us where the sun location is at. And then again, as I mentioned, the check angle process, this is what we actually want to use to determine Earth's surface. And I believe that the Greeks and Copernicus found this out, and that's why, again, Copernicus died, and then they released his information. And Aristophanes' lost notes, there's a story to tell there. Conduct the SIMO and setup of the globe model and FE models. We run both models in there. We use that through what? The test box. And it's actually a kill box for the globe. It is the test box wipes out the globe model. Operation Resolute Time and Golden Lance. Resolute Time right now ongoing. And again, I said we've broken that threshold of 45 degrees. We're at 46.5 degrees in April. The Golden Lance down the road, Mexico to Hawaii. And then last but not least, the actual sun distance. We showed you the sun distance calculator, how to actually figure out how far the sun is actually. It's just over 3,000 miles, not 93 million miles. Special message to educators in science. Join us in the Flat Earth community. Come out of the shadows of scientism and into the light to make this world a better place of hope, peace, love, and understanding for all of humanity. Final thoughts and analysis, and I put this slide in lastly. And that is, if we look at parts of past history on this subject, it's no wonder why the globe didn't take in the days of Aristophanes, and for good reason. His notes were probably intentionally lost. The Greeks figured out the Earth's surface was flat through triangulation and simultaneous observation. I really strongly believe that. Then in the days of Copernicus, it must have given him fits trying to solve the triangulation process. From two observers, the ball or sphere simply doesn't work when we apply a triangulation using the sun from two observers. In the end, Copernicus's work and his death, the pieces were put into play by others who simply thought they'll never do the math to figure it out, at least for now. But eventually, someone would. This concludes my presentation of SIMO observation and support of the Flat Earth model. If you have questions or if you'd like a digital copy of this presentation, you can email me at corey7fe@gmail.com. Again, thank you for watching, and be safe. God bless you all.